Excellent. So we are rounding out the hour or hours with a talk by Jason Williams on a topic that for those of us in the northwestern part of the country have seen a lot of this year. Jason's going to talk to us about snow and western juniper, I believe. And Jason comes to us from the Northwest Watershed Research Center, USDA Ag Research Service in Boise. Jason? Or drop the mic. That works too.
All right. Can everybody hear me okay? A no? I'll try to hold it. Better? Okay. All right. Things are off to a good start. Okay. So, and just one point of clarification. I guess I'm now at the Southwest Watershed Research Center in Tucson, Arizona. It's been a change since we rolled this paper out. That was led by Patrick Kormos. But what I'll be talking about today is not necessarily birds, but vegetation and how vegetation influences water, and then, of course, that can have implications for sage grouse. This is collaborative work between the ARS location in Boise, Idaho, and the location in Burns, Oregon. The work involves sort of selection of watersheds and instrumentation of those and collection of data, and then some modeling once we have that data in hand. So there's a lot of work across a number of individuals that you see here. This work was led by Patrick Kormos in our Boise office. So I'll just kind of start with the overarching goal, which is to better understand how juniper encroachment affects water availability for ecohydrologic processes and the vegetation attributes on snow-dominated rangelands, snow being a key element of the talk today. Then just by way of an outline here, we'll go over research questions. I'll talk a little bit about the watersheds themselves, the approach that we use here, which is using field collected data in concert with modeling effort. Then we'll go over some of the results and implications. This is kind of an iconic figure here from the Reynolds Creek Experimental Watershed showing the drifting of snow, and that's sort of an important piece of what I'll talk about today. Okay, so these are the study sites. We have 4 watersheds in southwestern Idaho, right along the Oregon border. Each of these watersheds are about 50 hectares in size. Some are larger, some are a little smaller. These sites are currently dominated by juniper vegetation, about 40 to 60% juniper cover on average. There are weirs at the outlet for each of the watersheds monitoring stream flow. We have 6 weather stations that you can see there. There are some symbols indicating the locations of those. Those are collecting a suite of meteorological variables hourly. Let's see, slopes are about 20%. Precipitation exceeds 600 millimeters, with most of that being as snow. And about 20% of that water then leaves the catchments as stream flow. We have extensive field collected data here, as well as some instrumentation and LiDAR data sets available for topography and vegetation. So our approach here to sort of characterize how snow is distributed on these sites and how that affects water is to develop a distributed model of snow accumulation and melt for juniper-dominated conditions and for sagebrush-dominated conditions. And then water availability is assessed through using time series modeling, so using that distributed data in a time series format to predict water delivery to the soil surface. So the model I'll talk about in a moment, it doesn't predict infiltration, but it predicts water available for infiltration and stream flow and evapotranspiration. And then we use that time series to derive an annual water budget, primarily the components of stream flow, evapotranspiration, and of course precip, which we're measuring and modeling. The model, which I'm not going to get into a lot of detail on, mainly because Patrick Kormos or Danny Marks would be better at explaining that to you. But this is a physically based model, the ice snowbow model, that we commonly refer to as the ARS snow model. It uses catchment topography and distributed meteorological forcings to estimate snow water equivalent, snow melt, and I have soil water input here. It's really water available for soil input or infiltration. The resolution for the model is at a 10-meter spatial grid with 1 hour time steps. And then it accounts for the influence of vegetation in terms of the radiation, its effect on wind speeds, and the redistribution of snow. So in the paper we provide a lot of detail on basically on how well the model performed relative to some measured data. Again, these watersheds are currently dominated by juniper vegetation, so we have a bunch of field measured data that we can actually use to sort of evaluate how the model performed for the juniper condition, and then we're using those data and what we know from some adjacent sagebrush communities to build a model for the same watersheds without the trees, so in a sagebrush condition. And so what you see here are some model results for snow water equivalent, the green lines, compared for each of the 6 climate stations we have there, compared with some measured snow water equivalent data from snow courses and snow surveys, which are the individual symbols there. So again, each graph there is an individual weather station, and we have 6 water years of data there. And overall, what you can see is that the model performed reasonably well relative to the measured data. There are a few places where it's under and over predicting, but overall we're very satisfied with the model's performance. Again, you can look at the paper for details on that. So now we'll start looking at some of the data. So here we're looking at data for snow water equivalent predicted by the model for both the juniper and the sagebrush condition. And again, here we're looking at differences in the amount of snow water equivalent associated with the snow distribution. For each of 6 water years, this is aggregated across all 4 watersheds. And the key things to point out here are the fact that for the juniper condition, we actually see higher snow accumulation, but that snow melts off a little bit sooner. So the green line is for juniper and the blue line is for the sagebrush-dominated condition. So sagebrush, we're getting perhaps less snow accumulation, but that snow is staying on the landscape longer. So perhaps even more important than how much snow we have is how it's distributed. And so one of the key, I think, elements of what we see from the modeling effort here is that for the juniper-dominated scenario, snow cover tends to be more uniform. That's the upper part of the graphic, the 4 watersheds shown there across the top. You can see the map is colored with snow water equivalent values more evenly than the graphic than the bottom of the graph that shows the sagebrush dominated scenario. So with the trees, wind speeds tend to be reduced and snow tends to form more uniform cover throughout the watersheds, whereas under the sagebrush condition with higher wind speeds, topography and vegetation interact to form these large snow drifts that tend to persist on the landscape for a longer period of time than the uniform cover under the juniper condition. So what does those differences in snow distribution mean for water delivery? I could have alluded to that already. This is a graphic of surface water input or water available for that. And what you see is that, as I alluded to in the previous graphs, there's more water available under the juniper condition, but the availability of that water is slightly delayed for the sagebrush scenario that we modeled here. So we'll now take a quick look at the water balance. So this is water balance derived from modeling of both sets of conditions. The bars in part A there, the top of the graph, are for the juniper condition, and in part B it's for the sagebrush condition. Again, this is a mixed sagebrush system that we've modeled, so there's some mountain big sagebrush and some low sagebrush in here. But what we really see between the 2 different scenarios we modeled is greater water available from the juniper vegetation, and then the condition with sagebrush, less water, but there's a greater allocation of water to evapotranspiration for the treed environment. For the sagebrush system, there's a greater allocation of water to stream flow in terms of its relationship or relative to the juniper model. So we'll take a little closer look at evapotranspiration here. So the green bars here represent the juniper model, and the gray bars represent the sagebrush model. And you can see that if we sort of run an average through there, it's about 300 millimeters of ET based on our modeling design here for the sagebrush, and then somewhere on the order of 400 to 500 millimeters for the juniper condition. So you can see much greater evapotranspiration under a juniper landscape. So here we can take a closer look at runoff, again with the green bars representing the juniper scenario we modeled and the gray bars representing sagebrush. And this just further illustrates the point that for the sagebrush condition, we're seeing a much higher allocation of water towards stream flow than for when the site is dominated by trees. This is across the 6 different water years there. Okay, so short and sweet. Really now just looking at the implications of this. Again, no pictures of birds and nothing to talk about specifically to birds here. But what we know about these sagebrush systems is they're very dependent on the pulses of water from snowmelt. Soil moisture patterns for sagebrush communities at this elevation, where the precip is snow dominated. Soil moisture throughout the year is strongly dependent on the spatial distribution of snow, as we might expect. But some studies tracking soil moisture conditions over the course of the year found that for almost every seasonal aspect of soil moisture, really you can link it back to where the snow was distributed and how much snow was accumulated. So snow is an important driver of soil water available for a host of processes here, including stream flow initiation, and the amount of water through snow input also affects the timing of stream flow cessation. So what we're seeing for these elevations is some persistence of snow through the forms of drift tends to prolong water availability for stream flow later in the summer season, which could be important as lower elevations tend to be losing snow, or they have less snow now than they used to historically. And then, of course, at lower elevations, sage grouse are feeling the pinch from cheatgrass and fires. So it may be important to retain these higher elevation sites where we can still get persistent snow forming in the drifts and have some prolonged summer stream flow that may have some downslope contributions to forming wet meadows and wetting up riparian zones, providing habitat, or at least in terms of providing food for habitat. So this work is highlighted in the Science to Solution article shown here from the Sage Grouse Initiative. I think there are copies on the table outside the door, as well as here's a snapshot of the paper here that's available in Rangeland Ecology and Management that's open access. And that concludes the talk, and I think we have plenty of time for questions probably. Yeah, go ahead, Rick. Yeah, that's a good question. So, I think so. I'd probably have to have Patrick in here to explain it specifically, because he modeled precip based on what we measured at the weather stations. But as the wind speeds are lower, the snow tends to drop out and accumulate and deposit there. There's probably some loss of snow with the wind blowing it out of the watersheds, perhaps, with the sagebrush. But we do see the drifts form under the sagebrush condition, so that probably has something to do with it. And then the earlier melt out from the juniper sites has to do with radiation from the trees, and also thinner snowpack there too. So. At this elevation, it's mountain big sagebrush. There's some low sagebrush on the site too on some of the aspects there. Yeah. Yeah. Yeah, so the question is, how are we accounting for the lack of snow under the trees? Yeah, that's a good question, and I don't, Patrick Cormos would probably be best to address how he dealt with that in the modeling context. Again, the precip that we're distributing here, we're measuring at a weather station, and we're using the model to distribute that, and it's a physically based model, so it's going to account for radiation effects of the trees and how that affects melt. So I don't know exactly how to specifically address your question other than to sort of tell you that's how the model is organized and developed for distributing snow on the site. But yeah, in the real world scenario, we know that there are pockets under the trees that may be a little more hollow than, sort of out in the open between the trees.
Not only are they barren, the tree canopy intercepts that snow and sublimates it back into the atmosphere, and that moisture never reaches the soil. And that can be a one-to-one relationship, the cover percentage of the juniper trees. So
Yeah, our experience on these landscapes, we talked a lot about that in developing the model, how to deal with the interception of snow. So the question was, or the comment, I guess, was the fact that the trees can intercept a lot of snow. And in this case, we're assuming that most of that snow that's intercepted, and this is based on our experience of being out on these sites, these are not extremely cold environments that snow tends to melt and plop through the canopy and drip down to the ground. And so we're assuming that the interception component and losses through interception are negligible in this environment that we have here. It's not the case in some colder environments where the trees will hold that snowpack for a longer time period. At least in the sites at the elevations that we're talking about here, in our experience, that most of that snow melts and just plops through the canopy. So in the paper we talk about that assumption and how that might affect the results and a number of other assumptions. Anytime you have a modeling exercise like this, there are a number of assumptions that you have to make, and we cover those in detail in the paper. Maybe we should have coffee and talk about this in detail.
on the stream flow increase in the Sagebrush system, did you also see a sort of a shift in the timing of when that flow occurred, from when the flow occurred out of the Juniper Woodland?
Yeah, so, and again, that's a modeled stream flow. But basically, the water available for that and the stream flow generation would be perhaps later in the sagebrush-dominated environment, but there would be a prolonged delivery of that water later in the summer relative to the juniper-dominated site. Does that answer your question? The question was, how might the differences in the two vegetation types affect the timing of the water delivery through stream flow? Yeah, thank you.
Well, that concludes our session on the special issue of REM that focuses on woodland encroachment into the Sagebrush Steppe and Southern Great Plains. I'd like to get another round of applause for all the speakers today, if we could. So this was recorded live, and all of these presentations will be available for download or at least viewing on the Sage Grouse Initiative website here in about a 3-week time frame. Thanks again for your attendance and attention today. Have a great rest of your conference. Thank you.